So far, we learned how to interpret the simple linear regression model y equal to beta 0 plus beta 1 x plus u. The relationship between x and y is linear. Beta 0 is the intercept parameter, and beta 1 is the slope parameter. But in many cases, the relationship between x and y is nonlinear. For instance, in the previous video, the relationship between the journal subscription and the journal price is not linear, and we use the logarithmic form for both x and y, and it has a better fit for the data. In economics, many relationships are also nonlinear. For instance, the marginal product of capital or labor is diminishing. And also, we have the hypothesis that the relationship between inequality and GDP is increasing at low levels of development, but then it will decrease. Similarly, the marginal utility from eating one more cake is decreasing as when you eat more cake. How to incorporate these nonlinear relationships in the regression model? Luckily, we can easily transform the data to represent many nonlinear relationships while still using the linear regression models. For example, we can model the diminishing marginal product by the linear log form or by the linear reciprocal form. We can also model the decreasing marginal utility or the decreasing growth rate as the quadratic form. So in this video, we will learn several nonlinear functions. Those are quite common for these linear regression models. After the video, I hope you can have a better understanding about the term linear in these linear regression models. What does that linear mean? Why we call it a linear regression model even if the relationship between x and y is nonlinear. The left figure shows how cubic functions look like. First, notice that these two lines are all increasing. The second thing to notice is that if you check their slopes, you will see their slope will change with the x. For instance, the slope is first decreasing, then increase again. For this line, the slope is first increasing, then it decreases. The right figure is the reciprocal functions. Depends on whether this beta 2 is larger than 0 or smaller than 0. We have increasing functions or decreasing functions. But the absolute value for the slope is always goes to 0. For this case, it's from the minus infinite to 0. But for this line is the infinite to 0, the slope. This is the log over log models. Remember that in the journal subscription example, we used the log subscription over log price. So this is how these two, the relationship between x and y look like. When beta 2 is larger than 0, both functions are always increasing. But when beta 2 is larger than 0, the slope is increasing. But when beta 2 is between 0 to 1, the slope is decreasing with the x. When beta 2 is smaller than 0, we have the decreasing relationship between y and x. Depending on the value of beta 2, we may have different types of this decreasing relationship. But if you check the slope, it's always from negative to 0. Another commonly used functional form is log over linear models. log y equal to the beta 0 plus beta 2 times x. When the beta 2 is larger than 0, we have the increasing function, and the slope is also increasing. But when beta 2 is smaller than 0, we have this decreasing function, and the slope is gradually goes to 0. The right-hand side of the figure is the linear log model. Now the y is the linear part, but x is in terms of the log x. So similarly, if beta 2 is larger than 0, we have the increasing function, and if beta 2 is smaller than 0, we have the decreasing function. And the absolute value for the slope is always decreasing. Let's check an example here. This is the scatter plot for the wheat yield from 1950 to 1997. The line here is the fitted value from the linear regression model. Overall, this line captures the trend of the observation. Some observations are higher than the fitted value, and some are lower than the fitted value. So we have this positive residual here and a negative residuals here. Let's check the regression results in R. If we regress the wheat yield in the place called Greenhoff over the x variable is the time, and we check the summary of these regression results, the coefficient is 0.02. Even though the value is very small, but it's economically significant. We will learn this economic significance later. We talked this point before. This coefficient can be large or small depending on the scale of the data. The R square is 0.65, which is pretty good for the goodness of fit. But if we check the residual over the time, which is the x variable here, we can see that residuals first are positive, then negative, then positive again. The ideal case for the residuals would be they should be randomly positive or negative. They should have like sequences of positive and sequences of negative residuals. So the ideal case could be here, 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 here. Just randomly over the x. So these positive and negative blocks of residuals imply that the linear specification we use may not be appropriate. How about alternative functional forms for the regression? For example, if we use the cubic form, here is the regression results. The reason we think about the cubic form is that the function has the pattern that the slope can decrease first and then increase again. The regression is similar. First, we make a new variable, time 3, which is the cube of time. Then we can run the regression and check the summary. Now the R square is 0.75, which is already bigger than the linear model. So it means we have a better fit with the cubic function. This is the scatter plot of the sample and the fitted line yi hat over the independent variable x, which is the time. Compared to the previous scatter plot, we have a better fit. The residuals are smaller and they are more randomly larger or smaller than zero. Notice that the x-axis is still the variable time, not the cube of time. If we plot the cube of time over the fitted value yi hat, then we will get the linear line again. Similarly, if we check the residuals over the independent variable time, we have more balanced positive and negative residuals. There is not many rounds of positive and negative residuals. How to interpret the coefficients in nonlinear specifications. The more details can be found in the appendix of the Principle of Econometrics, but the idea is to take derivative of y with respect to x. For instance, in the simple linear regression model, if we take partial derivative of y over x, we get beta 1. So we interpret beta 1 hat as following the similar idea. If the specification is cubic, we just take the partial derivative of y over x, then we get this. So we interpret it as a 1 unit increase in x is associated with this amount increase in y. For the quadratic form, if we take the partial derivative of x, we have beta 1 plus 2 beta 2x. So it means 1 unit increase in x is associated with a beta 1 plus 2 beta 2x increase in y. For the linear log models, it's the same idea, but now from this we can rewrite it as delta y is around beta 1 times x times delta x. These two terms is similar to the percentage change of x. So the interpretation of coefficients in this linear log model is that a 1% increase in x is associated with a beta 1% unit increase in y. Another example is the log linear model. It's the same, just flip the x and y. In this case, it's 1 unit increase in x is associated with 100 times beta 1% increase in y. For the log and log model, both sides are percentage change. So it means the 1% increase in x is associated with a beta 1% increase in y. So this log and log linear model means that this beta 1 hat we estimated is actually the elasticity of y respect to x. Here is a summary for the interpretation of beta 1 for 4 different nonlinear specifications. For the level and level model, the unit change of x is associated with beta times this unit change of y. For the level log model, this percentage change of x is associated with the unit change of y. An opposite one is the log level model. In this case, which is the unit change of x is associated with this amount of the percentage change of y. And for the log and log model, both sides are percentage change. Okay, that's all for video 3. Record the question at the beginning of this video. What is linear mean? It is actually not describing the linearity between x and y, but to describe the linearity of parameters. The regression equation is linear in the parameters beta 0 and beta 1. There is no restrictions on how y and x are defined, but pay attention to the interpretation. Different forms of x and y imply different coefficients and different interpretations.